Ever wondered what's really going on inside those tiny little chips that basically run our entire world? Well, today, we're going to crack one open, metaphorically, of course, and take a deep dive into the architecture of a microcontroller. We're going to uncover the brilliant design choices that make our digital lives tick.
So think about it for a second. You tap an icon on your phone and an LED blinks. Simple cause and effect, right? But in that tiny fraction of a second between your touch and that light, there's this hidden universe of high-speed decisions happening. So what is the chip actually doing in that instant? That's the big question we're going to dig into.
All right, we've got 5 key stops on our tour. First up, we'll look at the CPU's most basic job. Then we'll explore 2 competing blueprints for how these chips are even designed in the first place. After that, we'll uncover a really cool tool called the stack, learn the delicate art of flipping a single bit, and finally, we'll see how it all comes together on the data superhighway. Let's get into it.
Okay, let's start at the very beginning. At its heart, a processor is basically a machine that follows a recipe. But, to do its job, it needs 2 things. It needs the recipe itself, we call those instructions, and it needs the ingredients to work with. That's the data.
It's just this constant, simple loop. Get an instruction, then get the data for that instruction, over and over again. Sounds pretty straightforward, right? Well, this creates a really fundamental design challenge. How do you organize your memory so the CPU can grab both of these things as fast as humanly or siliconly possible? So the classic answer to that question is something called the von Neumann architecture. It's named after the genius John von Neumann, and his design keeps things really simple. It basically says, hey, let's just put everything, our instructions, our data, all of it, into one big shared memory space. It's flexible, it's relatively easy to build, makes sense.
But, and there's always a but, that simplicity comes with a price. What we're seeing here is a traffic jam. Because there's only one single path to that memory, the CPU has to wait in line. It goes and fetches an instruction, then it has to get right back in the same line to fetch the data it needs for that instruction. This delay, this traffic jam, is famously known as the von Neumann bottleneck.
So, what's the alternative? Well, that would be the Harvard architecture. This design takes a totally different approach. It says, why have one road when you can have 2? It creates completely separate memory and totally separate data paths, one for instructions and one for data.
And this brings us to a classic engineering trade-off. On one hand, von Neumann is simpler. It's more flexible, which is awesome for general-purpose computers like your laptop. But Harvard, by letting the CPU grab an instruction and data at the exact same time, is way, way faster. This makes it absolutely perfect for microcontrollers in things where speed is critical, like your car's engine or your smart thermostat.
Okay, so we've seen how the memory is organized. Now let's peel back another layer and look at a different design choice, the instructions themselves. Do you want them to be simple or do you want them to be complex? This brings us to a huge debate, RISC versus CISC. RISC, which stands for Reduced Instruction Set Computer, uses a really small vocabulary of very simple instructions. Each one is designed to be executed incredibly fast. The whole goal is to make each individual step as quick as possible. CISC, or Complex Instruction Set Computer, is the complete opposite. It uses these powerful, complex instructions that can do multiple things all at once. The goal here is to use fewer instructions to get the same job done.
And this table just lays out so clearly how that difference in philosophy plays out in the real world. Just look at RISC processors, like the ARM chip that's almost certainly in your phone. They have simple hardware and try to get everything done in just one clock cycle. This is amazing for power efficiency and battery life, even if the code ends up being a little bigger. But then you have CISC processors, like the x86 chip in your laptop, with more complex hardware. Their instructions can take multiple cycles, but it results in smaller code. It's a really fascinating contrast that directly impacts how our favorite gadgets perform.
Okay, so we've seen the big picture architectural blueprints. Now let's zoom way in on a wonderfully clever tool that programmers use every day to manage data and control the flow of a program. Let's talk about the stack. The best way to think about the stack is like a stack of plates at a buffet. When they bring out a clean plate, you push it onto the top of the pile. When you need a plate, you pop the top one off. In computing, the stack works exactly the same way with data. It's a last-in, first-out system. And it's incredibly useful for things like remembering where a program needs to return to after it calls a function.
Now, here's where it gets really cool. In modern microcontrollers, like the PIC-18 series, the stack isn't some hidden, off-limits thing anymore. They give you direct hardware access. You get special registers that let you literally see and even change the data sitting at the top of the stack. And another register always points to exactly where that top is. This basically turns the stack from a simple plate dispenser into a programmable power tool.
And hey, don't just take my word for it. As Microchip, the company that makes these controllers, says, this direct access opens up some truly unique programming possibilities. You can actually manipulate the return addresses of your functions on the fly, which lets you create incredibly efficient and clever software, kind of like building a tiny operating system on a really simple chip. It's wild stuff.
So we've seen a tool for managing big blocks of data. But what about the absolute smallest piece of information there is, a single bit? Well, let's look at a tool that's designed for pure surgical precision. This feature is absolutely incredible. It's found in a lot of ARM processors, and it's called bit banding. The concept is kind of mind-bending, so stick with me. The hardware takes a big chunk of memory, and it gives every single bit inside that memory its own unique address. Imagine giving every single light bulb in a skyscraper its own personal light switch down in the lobby. That's bit banding.
So, why on earth would you do that? Well, because it allows for something called an atomic operation, one that is indivisible, one that cannot be interrupted. See, normally to change just one bit, a program has to read a whole chunk of memory, carefully modify that one bit, and then write the whole chunk back. If another process interrupts that sequence, you can get all kinds of errors. With bit banding, you just write to that bit's special address, and the hardware does the entire operation instantly and safely. No extra code, no risk.
Here's exactly how that works. Let's say we have some data in memory, and we want to change just one little bit from a 0 to a 1. Instead of messing with the original data, we just write a 1 to that bit's special, unique address, its alias. And poof, the hardware instantly and atomically updates the original data for us. It's like having a dedicated hardware switch for every single bit. It makes controlling hardware super simple and incredibly safe. Okay, we've seen the core, the memory architectures, and some really cool specialist tools. But in a modern chip that has dozens of different components all running at once, how do they all talk to each other without causing a massive gridlock traffic jam? The answer is something called a bus matrix. The best way to think of it is as a highly intelligent multi-lane superhighway inside the chip. It's basically an internal switchboard that can connect multiple masters, things that start data transfers, like the CPU, to multiple slaves, things that hold the data, like memory or a USB port. And it can do it all at the same time. And this just brilliantly shows you the power of that bus matrix. I mean, look at what can happen all at once inside a modern chip. The CPU is off fetching its instructions, while at the same time, USB data is coming in, Ethernet data is going out, graphics data is being shot to the screen, sensor data is being loaded into memory, all of it at the same time on parallel paths. This is what makes our modern, responsive devices even possible.
So at the end of the day, the crucial takeaway is that this internal superhighway makes sure that a really busy component, like the part handling your graphics display, doesn't hog the road and slow down the main CPU. Without this, your phone would lag and stutter every time you tried to download a file while watching a video. The bus matrix lets every part of the chip work at its absolute best all the time. Which, of course, leaves us with one final thought. As our devices demand more and more performance, and we cram more and more components onto a single piece of silicon, the challenge of managing all that data traffic just becomes immense. So, are we going to solve it by building even smarter, more complex bus matrices, these superhighways, or will we eventually need to throw out the rulebook and invent entirely new architectural blueprints to keep everything moving? The answer to that is going to define the next generation of all our technology.